Welcome to Introduction to Quantum Field Theory, Lecture 20. In this lecture, I will be talking about vertex corrections in quantum field theories. As a review, recall that in Lecture 17, we considered the full propagator as the two-point function weighted with the full action S. And we considered an expansion of this full propagator in perturbation theory in this same lecture. The propagator was introduced as a two-point function because there are two fields phi inside the path integral. So in this lecture, we will discuss the four-point function where we have four fields phi inside the integral, and we will call the corresponding object gamma 4 for the four-point function, and we'll talk about a perturbative expansion of this object. As with the case of the propagator, we are particularly interested in the connected four-point function, meaning those diagrams that only have contributions from pieces that have no disconnected parts. For a four-point function, the minimum number of vertices to connect four fields is one vertex, because if there is no vertex, then you have to connect the four legs such that there are just two lines, and two lines don't interact with each other, so you have, by definition, a disconnected diagram. So the leading order perturbative contribution to the four-point function is given by the first order perturbative result, where we have minus Si appearing in the side path integral here. We can use Wick's theorem to calculate the contribution in terms of just the contributions that involve propagators. And since we have a four-point vertex in the action Si, and we have four legs here, we can count the possibilities of how many contractions we can do. And we find that in total we have 4 factorial versions to connect the pieces together. That brings us a 4 factorial in the expression for the first order perturbative result for the four-point function. And then we have the 4 propagators that start at the different locations x1, x2, x3, and x4, and they all end up at the point x. Of course, we can use momentum space transformation to represent that propagator, to represent the four-point function. If we use the momentum space representation of the propagator that we wrote down in equation 15.9, we find that that same expression for the four-point vertex is given as an integral over momenta p1, p2, p3, p4, times the 4 propagators at those same momenta, times a delta function and an exponential that just represents the Fourier transformation. Note that the delta function that appears in this case here is just a consequence of momentum conservation, because our setup for the field theory is fully relativistically covariant. The result for the individual observables, such as the four-point function, will respect Lorentz symmetry, so momentum will be exactly conserved. And this this delta function inside this integral just represents the fact that the sum of all momenta, if they are all incoming, have to even out to 0. Similarly, since we are dealing with a four-point function, there must be 4 propagators that appear in the expression for the connected four-point function. These just represent the fact that in a diagrammatic way, we have 4 legs that 4 external legs of a Feynman diagram. Now, similar to the case of the propagator, we can take advantage of the fact that this is just effectively a Fourier transformation in variables p1, p2, p3, p4. Here is the exponential and some integrand here. So if we do a Fourier transformation of this object with respect to the 4 momenta p1, p2, p3, p4, we can define a momentum space correlation function. And we can not only do this for the first order perturbative result, we can do this for the full 4-point function, gamma 4. So in momentum space, we can always express the 4-point function as functions of the momenta, P1, P2, P3, P4, of the individual 4 legs that come in. And this is just the Fourier transformation of the full 4-point function that we started out with. Again, because of the fact that we have 4 external legs, there must be 4 propagators in momentum space appearing in this expression, and there must be a delta function, such as this delta function here, that ensures that momentum is exactly conserved. For the expression of the first order perturbative vertex that we calculated, if we do a Fourier transform of this and essentially neglect the 4 propagators that are just a trivial consequence of the fact that we have 4 legs, and the delta function that's just a consequence of momentum conservation, we find that the only non-trivial information of the momentum space 4-point function is given by this coefficient -4 factorial lambda. And we'll call the operation of neglecting the 4 propagators and the momentum space conservation delta function as amputated vertex function. So anytime we say amputated, it just means we neglect these pieces. So this obviously works in a trivial way for the first order perturbative vertex, but we can, by the structure that we just discussed for the full vertex, also repeat this procedure for higher order perturbative contributions. Let's look at one of those higher order perturbative contributions. Let's look at the next to leading order contribution in perturbation theory that is sometimes also called the NLO for next to leading order term. In this case, we have an additional sort of contribution that comes in with 2 powers of SI, and the 2 powers of SI are just expanded in terms of integral over x and y times phi 4 of x, phi 4 of y. In order to evaluate this, we want to use weak contraction again. So we're going to have to connect external legs to these 2 vertices that each have 4 legs. So if we start by picking out phi of x1 and want to attach it to some of these internal vertices, we first have to have the choice of attaching it to either phi 4 of x or phi 4 of y. That gives us a factor 2. And then for each of those, we have 4 fields phi. So we can, for instance, attach it to phi 4 of x. So this gives another factor of 4 for the 4 operators that we have in phi to the 4 of x. Once we have attached phi of x1, we next pick phi of x2. And if we want to attach it to the same vertex as phi of x1 is attached to, then we have 3 legs out of the phi cubed of x that we still have left after having performed the first contraction. So once we've done that, we can pick one of the phi of x that we have left and attach it to one of the 4 phi of y's. That gives us a factor of 4. Then pick the last phi of x, again attach it to phi of y. That gives us a factor of 3. And finally, we attached it to external legs phi of x3 and phi of x4 to the phi squared that we still have left. That gives us another factor of 2 and completes the attachment. In this case, the overall factor is 1/2 times 2 times 4 from the first contractions times 3 from the next contraction times 4 times 3 from the next contraction times 2 from the last contraction. That happens to be 4 factorial squared divided by 2. Now note that in this process of attaching lines, we made a particular choice when we said that we want to attach phi of x2 to the same vertex that phi of x1 is already attached to. We could have made 2 different choices that happen to sort of lead to also contribution to the amputated connected 4-point function. It so happens that these other choices give exactly the same result, where we just exchange the labels x1, x2, x3, x4. So in total, basically, we have 3 times the same expression that we just found when we said we want to attach phi of x2 to the same vertex as phi of x1. Having done so, we can again define the amputated connected 4-point function in momentum space. And from the contractions, we find all the respective free propagators that we have to evaluate. And it turns out that we find for these first contribution, where we have attached phi of x2 to the same vertex of phi of x1, gives this following integral contribution to the second order amputated connected 4-point function. And then there are the 2 others where we sort of attach phi of x2 to other vertices. For us, one of the more interesting cases will be that we consider the 4-point vertex at vanishing external momentum. So unlike the leading order piece here, the second order perturbative expression for the 4-point function does depend explicitly on 2 of the momenta that come in from the external legs. But we can consider a special case where we set both of those momenta and also the other 2 momenta to 0. This is the case. The integral here simplifies, and we just get an integral over 1. We just get an integral over the propagator squared, essentially. It's easiest to evaluate this remaining integral at 0 temperature. We can do so easily by, again, reminding ourselves that we have defined this function phi in lecture 10. It was defined in this particular way, where mu, again, is the renormalization scale that is important whenever we go to the dimensions that are not exactly equal to 4. And the result is this expression here that involves the gamma functions. So if we then use this phi function here, we find that this is precisely the integral that's appearing in the connected 4-point function. So if we set d is 4 minus 2 epsilon, we have a result for the connected second order perturbative expression, 0 momentum. There's a finite term at leading order, and then there is a divergent term at next to leading order. It's divergent because the gamma of epsilon tends to infinity once we send epsilon here, the regulator epsilon to 0. So the connected amputated 4-point vertex is divergent. We can expand in powers of the regulator epsilon, and we find an expression that has the familiar structure, familiar from renormalization, that's given in this equation 20.12 here. In order to get a finite result for the 4-point function, we need to renormalize the coupling constant. And we do that in complete analogy to what we discussed in lecture 17 on mass renormalization. So we take the freedom that in our Lagrangian, the parameter lambda is not necessarily the same as the physical coupling. We replace it by the following expression. We replace lambda by lambda physical plus a counter term delta lambda, where we expect delta lambda to be given by an expression that's already order lambda squared or higher. And it turns out that if we choose delta lambda, the counter term, to be given by this particular value here, we can make the connected amputated 4-vertex finite. So the result we get is given in equation 20.15, where again, there are divergences, but at higher order decoupling that would have to be canceled by higher order counter terms again. And we have this particular result here that would depend, so it seems, on the renormalization scale mu bar. Recall that mu bar is an arbitrary scale, and the 4-point function is, at least in principle, a measurable quantity. You can do, for instance, a scattering experiment, and the scattering experiment cannot depend on an arbitrary scale that you don't know about. So that means that the left-hand side is independent of mu, but it seems like we have an explicit dependence on mu on the right-hand side. And the obvious resolution of this is that somehow lambda physical decoupling that we have in the Lagrangian must implicitly depend on mu as well to cancel the dependence here. So long story short, we know, because this is a physical quantity, that the 4-point function cannot depend on mu, so the derivative with respect to mu must be 0. In order to cancel the explicit dependence that we found on mu in this result here, lambda physical has to be dependent on mu bar, and that if we set lambda physical to be a function of mu bar, we find that lambda physical has to fulfill the following differential equation. This is just plugging in lambda physical of 0 in the expression for the connected 4-point function and taking this derivative here. To leading order and perturbation theory, just go back. Here we have something that is formally higher order than the one here, so we can neglect this piece, and we find that to leading order and perturbation theory, the derivative of lambda physical has to be 3 lambda physical squared over 16 pi squared. And of course, there are higher order perturbative corrections that we don't write in this equation. Nevertheless, this just means that the change of lambda physical with respect to mu is not 0. The coupling changes with respect to the scale. In the linear of quantum field theory, we say it runs. We will explore the consequences of the running coupling in the following lecture, and we'll discuss the details of how that ties into the so-called renormalization group also in that lecture. And this concludes the presentation.